Hello, my name is Vicente Jr. and today I'm going to be presenting my completion of coursework to get a degree in mechanical engineering. First I would like to greet my advisor, Professor Kleber, Vieira de Paive, as well as my Coorientator, Marcia, Barbosa, Henriques, Mantelli, and also Gustavo Jorge Nuremberg, which is going to help evaluating this work. I'm going to be presenting about the thermal behavior of pulsating heat pipes in condition of gravity and microgravity. This is the summary. So first I'm going to start with a brief introduction about I'm going to talk about why we're doing this, and I'm going to explain about the device, and then I'm going to talk about the heat pipe and microgravity, and specifying a little bit more, I'm going to talk about the pulsating heat pipe, which is the device we're creating. And then the second part of the presentation, I'm going to show you results, the ground tests, and I'm going to talk about the test aboard the suborbital rocket and the conclusions. So not long ago, a computer with a small processing capacity could occupy a moderately sized building. Nowadays, though, there are compact computers available on the market with a higher computing velocity and processing power. This all became possible for the development of electronic components that became exponentially smaller and more efficient in time. However, the components dissipate heat that can lead to overheating hardware and long-term damage. So new technology is necessary to accommodate for thermal dissipation, which historically was solved by installing large fans next to computer processing equipment. The necessities of minimizing electronic components are especially important and very closely monitored in the aerospace industry, where costs of launching space vehicles are determined by an exponential function determining the mass of the vehicle to be launched. The thermal control of electronic components in space is potentially more complicated when compared to systems on Earth. Once upon space, the vacuum-like atmosphere does not allow the transfer of convection heat, like in this picture. The heat pipe technology is an alternative to control and regulate thermal heat in space because its functioning does not depend on the gravity. Pulsating heat pipes are characterized by the following basic settings. They have a heat pipe circuit arranged to form a closed loop, like in the picture. No capillarity structure inside the tubes. There must be at least one heating observing region, which is the evaporator, and one heat rejection region, which is the condenser. And the adiabatic region located in between them both is optional. In order to organize the flow and increase the heat transfer, some surface treatment techniques will be investigated in this experiment. The inner surfaces of the pulsating heat pipes are coated alternately with a material that alternates the wettability of the fluid, making the wetting hydrophilic or hydrophobic. Heat pipes and microgravity. The heat pipes are highly efficient heat transfer devices. Essentially, it is a metallic evacuated tube closed at the two ends, like in the picture, containing a fluid and its interior that is called working fluid. The tube might be divided into three distinct regions, as I just said: the evaporator, which is this part in the picture right now, the condensator, and the adiabatic region. The heat supplied to the tube on the evaporator creates a pressure difference, and that's how the fluid moves. So for the evaporator, he's going to move towards the condensator, and then here he's going to be cooled down, and he's going to return by this capillarity structure back to the condenser. the transportation liquid by this capillarity structure is called the capillary pumping effect, and that's one of the reasons that we don't need gravity to make those devices work. Creating microgravity. So, in a practical sense, microgravity can be achieved with several technologies, each depending upon the act of free fall. Each procedure is different from each other by the cost, level, and time of microgravity. And there are basically 4 techniques: the drop towers, the aircrafts, the rockets, and satellites or space stations. The drop towers are essentially a hole in the ground. It accommodates large experiment packages, generally using a drop shield to contain the package and isolate the experiment from aerodynamic drag during the free fall. Air is pumped out of the facility until a certain vacuum is achieved. By doing so, the acceleration effects caused by aerodynamic drag on the vehicle are reduced. This image is a 490-meter deep vertical mine shaft in Japan that has been converted to a drop facility that can achieve 10 to the negative 5 power gravity environment for up to 11.7 seconds. A second way to produce microgravities is using aircrafts. The aircrafts, they can get a low gravity for periods of about 25 seconds or longer. Although airplanes cannot achieve microgravity conditions as high quality as those produced in drop towers, they do offer an important advantage over drop facilities. The experimenters can ride along with their experiments. Typically, one flight lasts 2 to 3 hours, and they can do 40 parabolic trajectories. And during those parabolic trajectories, they get environments of 10 to the negative 3rd power gravity environment. Small rockets, they provide a third technology for creating microgravity. A sounding rocket follows a suborbital trajectory and can produce several minutes of free fall. The period of free fall exists during the coasts, after burnout, and before entering the atmosphere. Acceleration levels are usually at or below 10 to the negative 5 gravity. This picture shows a couple of rockets differentiating in size and time of microgravity. So the Texas with 16.2 meter stall, it's this one. He flies over to up to 705 kilometers and can get levels of 12.5 minutes. He gets microgravity for 12.5 minutes. The rocket we're flying our experiment in, he can get up to 6 minutes of microgravity. Yeah, although airplanes, drop facilities, and small rockets can be used to establish a microgravity environment, these laboratories share a common problem. After a few seconds or minutes of low gravity, Earth gets in the way and the free fall stops. So one of the best ways to test experiments for days, months, years is by using satellites or space stations, such as the International Space Station. Pulsating heat pipes. So the pulsating heat pipes, they were introduced in the mid-90s, and they're relatively a new type of heat transfer device, which may be classified in a special category of heat pipes. It is, as I said before, a closed-loop pulsating system. Thus formed is evacuated and subsequently filled up partially with a pure working fluid. The optimum quantity of working fluid needed depends on various parameters and is still an area of research. The entire essence of a thermomechanic physics lies in a constant volume, a two-phase bubble liquid sludge system formed inside the tube bundle. due to the dominance of surface tension forces. This tube bundle receives heat at one end and it's cool at the other. The temperature gradients give rise to temporal and spatial pressure disturbances in the wake of change phenomena. The generating and the collapsing bubbles. So first, the bubbles, they're generated and they grow in the evaporator, and simultaneously they collapse in the condenser. And the generating and collapsing bubbles act as pumping elements, transporting the entrapped liquid slugs in a complex, oscillating, translating, vibratory fashion. A direct consequence of the thermohydrodynamic coupling of pressure and temperature fluctuations with the void of a fraction distribution. This causes the heat transfer essentially as a combination of sensible and latent heat portions. And in the study of art that we're going to discuss next, we're going to talk about if it depends more on sensible or latent heat portions. Study of art. Pulsating heat pipes is a promising technology for dissipation, high-grade heat, and has wide variety of applications. The considerable interest in such a heat pipe is due to its simple structure and high heat transfer performance. Therefore, extensive experimental investigations and theoretical analysis have been carried out to study the influence factors of pulsating heat pipes. W, Q, and H.B. Mudd and his teams, they figured that rougher surface could improve the startup performance of the pulsating pipe. Ling and his group, they studied the operating mechanism and slug oscillating motions of pulsating pipes through the image recorded by a high-speed camera, and it was found that more bubbles emerged and grew up in the sharp corner, and the growth rate of bubbles increased with heat input. The liquid slug displacement, velocity, and frequency all increased with the heat input. Fumoto and his group, they found that the self-rewetting fluid improved heat transfer characteristics in the evaporator section. Song and Shu, they performed tests on pulsating heat pipe with 4, 6, and 9 turns, and they figured that it might not work at the exact horizontal position. However, the 3 pulsating heat pipes, the pulsating heat pipe with 3 turns could operate at slight inclination angles. The heat transfer performance of the pulsating heat pipes increased in the number of turns, and the heat performance was generally better in the vertical hidden mode. Xian and his team, they studied the effect of working fluid on the heat transfer characteristics of pulsating heat pipe, and it was found that the pulsating heat pipe with water as a working fluid showed a better performance and more stable heat transfer characteristics than the pulsating pipe with ethanol as a working fluid. Kandekar and his team investigated the influence of filling radio and heat mode on the heat transfer performance of a pulsating heat pipe. The slug pulsating action was observed in the filling radio range of 25 to up to 65%, depending on the working fluid. The pulsating heat pipe with a small number of turns could not operate in a horizontal mode. Thompson and his team studied the effect of operating mode, heat conditions, working fluid, and high gravity on the thermal performance of the 3-dimensional flat plate pulsating heat pipe. It was found that the pulsating heat pipe operating in its bottom heating mode provided better heat transfer performance than when operating in its side heating mode. The reduction in heating area decreased the thermal performance, and using water as a working fluid provided the lowest thermal resistance. Caro and so on and Terton, they found that the thermal performance of a pulsating heat pipe improved by increasing the evaporator temperature, decreasing the evaporator effective length, and increasing the turn number. G and his team found that the oscillating motion in a pulsating heat pipe with a super hydrophobic surface could be generated. Ling and his team investigated the effective range of pulsating heat pipes with 4 turns and found that the inner diameter should be higher than 0.08 millimeters with working fluid of water in a vertical heating mode. Chim and his team investigated the thermal performance of pulsating heat pipe with a non-uniform channel and found that closed-looped oscillating heat pipe with a non-uniform channel was functional to all inclinations when the filling ratio was above 50%. Sheffy and his team established a thermal model for the behavior of a liquid and vapor plugs of a pulsating heat pipe, and the results show that the heat transfer in pulsating heat pipes mainly depended on sensitive heat. Alright. The internal diameter in a parameter which necessarily affects the very definition of a pulsating pipe. Beyond a particular limit, all the working fluid will tend to settle down by gravity, and the device will stop functioning as a pulsating pipe. So these folks, they published an article where they analyzed the effect of a tube inner diameter for a pulsating pipe operating in a vertical position. The study shows that for a given number of turns, the performance improved with the internal diameter. Further, doubling the diameter did not double the performance. At the same internal diameter and evaporator length, the performance is higher with increasing the number of turns. Thus, for a specified temperature gradient between evaporator and condenser, the performance can be increased by increasing the tube inner diameter and or the number of the emitting turns. The goals of this work, though, was not to study the effect of the inner diameter on the pulsating pipe performance, but we took in consideration previous studies and decided for using an inner diameter of 3 millimeters, which is about the limit for its functionality as a heat pipe when using water as a working fluid. The effect of hydrophobic and hydrophilic and hydrophobic surfaces. So these folks, they studied 3 different tubes: the hybrid, the regular, and the super hydrophobic tubes. The hybrid surface oscillating heat pipe had a lower startup temperature and showed better heat transfer ratio. So the way they were organized, the hybrid one had a hydrophobic surface on the evaporator and a hydrophilic condenser. The regular one had no chemical treatment, and the hydrophobic one had just a hydrophobic evaporator. So what happened was, in the hydrophobic evaporator, the evaporator dried out because of the wettability was super low, and then the temperature is raised up and the tube does not work as a pulsating heat pipe. The way we are gonna do the treatment, the chemical treatment in our tube is like on the image. First we divided the channels in separate parts. The first part would be hydrophobic, the second hydrophilic, third hydrophobic, and we are alternating this. So now we're gonna go to the manufacturing process. So we buy copper tubes with 3 millimeters diameter, and we press them against a matrix to shape them with this U-form as shown in the picture. After that, we have to clean the tubes. We use soap and water, sulfuric acid 10% concentrated, and we wash it with this sponge, and then we rest it for about 5 minutes in an ultrasound bath. After that, we have to attach to the tube a thing called umbilical that's going to be used to fill the tube with the working fluid. And the way we do it, we weld. And after it's welded, we repeat the cleaning process, the 3 steps. And then we prepare the tube for the vacuum. First, we put in a pump that can get a low vacuum. And to make sure the vacuum is going to be kept inside the tube, we use a liquid detector. So we spray helium particles on the tube, and if the machine indicates any variation on the vacuum, that means that the welding is imperfect and we have to redo it. If the welding is good, then we go to a second pump, which is more powerful and can get levels of 10 to the negative 6 millibars up to 10 to the negative 8 millibars of pressure. And that's the level of pressure we want to have inside for the pulsating heat pipe work flawlessly. And then after making the vacuum, we close temporarily the tube with a scissor, and we use this structure shown in the picture to fill the tube with working fluid. Alright, so now we're going to go to the second part of the presentation. We're going to start with the ground test, the test aboard of this Barbosa rocket, and the conclusions. So the first test we performed was with 25% filling radio on the bottom heating mode, which means the vertical mode, and this is the graphic that we obtained. Gradual input power was added from 10 watts, the second level was 20 watts, and then 30 watts, 40 watts, 70, 100, 140, 180, 220, 360 watts, and 300 watts. Every level we waited about 600 seconds, which is 10 minutes, so the flow could get to the steady mode, steady flow. So for this configuration, we observed an average of 300 watts. The average for 300 watts of heat input, it's 53 Celsius degrees. So it's really good. You can see that the tube is working. And this is the graphic for heat input to the total thermal resistance of the tube. The best performance in this position was for 220 watts. The total resistance of the tube was 0.046 Celsius per watt. And this is the graphics that we're comparing when you gradually add heat input to the tube and you abruptly add heat input. So the first graphic, we set 3 levels of power, which is 100 watts, 220 watts, and 300 watts. and if you observe these lines over there, you can see that, so this is the line for 100 watts, and this is the line for 100 watts again. So 100 watts, 220, 300, 220, and 100 watts. You can see that the graphic is not symmetric. This part, it's different than this one, and this happens because there's a period that the fluid takes to get to the steady flow. So right here, the oscillation is kind of aggressive, and here when the tube is already working as a pulsating heat pipe and it's cooling down, you can see that it works differently and it works better. The average temperature here is like the resistance here, it's way better than in the first half. Alright. So continuing, this is the 25% filling radio, but now on the horizontal orientation. You can notice that when we are this is this is incorrect. So this is the graphic with the gradual heat input, and we can see that on the 2,400 seconds mark, the tube tries to oscillate, but it cannot keep it up, and then the temperature just goes up to 200 Celsius degrees, and it doesn't work as a pulsating heat pipe. Same when you're adding abruptly, like the first level was 100 watts, second level we have to stop because the temperature is going so high that we would damage the device. So this proves that for 25% filling radio, the gravity has a big impact, and the evaporator dried out. For 50% filling radio, we found similar results to the 25% configuration. The pulsating heat pipe worked well, doing its range from 100 watts to 300 watts. The average peak of temperature was about 56 Celsius degrees, which is pretty good. And this is in the bottom heating mode. And then when we flip it over and we perform the test on the horizontal orientation, the tube could not work without the gravity help. And you can see that the results here are a little bit better than the 25. The tube tried to pulsate at certain polymer levels, but it cannot keep it up and it doesn't work. So this is when we are trying to gradually put heat input, and this abruptly. Yeah. And finally, the 75% filling radio bottom heating mode, we can see that for 2,400 seconds in 40 watts, the tube started working as a pulsating pipe, starts like pulsating pretty well, and the temperatures are kept low. And in this configuration, the best performance happened at 300 watts with a resistance of 0.066 Celsius per watt. And yeah, here's just a comparison between gradual and abruptly heat input on the tube. Again, the graphic here is not symmetrical. The first half oscillates differently for 100 watts, and then when it's cooling down, the oscillation is more steady and clear. And finally, like the most exciting result is for 75% filling radio on the horizontal orientation. The tube works as a pulsating and starts pulsating at 2,400 seconds, which is 40 watts and not 400 watts. The performance was super exciting because it worked in the horizontal orientation for the first time. So that means if it went in space, it would work. And this is the graphic of the total resistance per heat input. And the total resistance of the tube reached 0.1 Celsius per watt in the levels of 220 watts and 300 watts. This is a little bit more than the one achieved in the vertical position, or in comparison to the 25% filling radio is also a higher resistance, but it's still pretty good and it works without the gravity. Yeah, this is the comparison of adding heat input abruptly and gradually to the 75% filling radio on the horizontal mode. And you can see again, this is not steady, this is not like symmetrical, it's a little bit more symmetrical though. And yeah, that's because of the time for the tube work as a steady flow. And then the test with chemical treatment, we used copper cylinders glued with torso glue. And for the chemical treatment, we used glycol zero. And there was a couple problems with that because the torso glue, it's not super resistant to vibrations. And when we put the tubes against our metrics to shape them correctly, probably there some holes were created, and it was super hard to find the holes. So the levels of vacuum achieved, they're below what we expected, like 10 minus 1 millimeter bar. And then, as we were not trusting the results, we did two tests. So the first test, this part of the test is like the test with chemical treatment, and this part of the test is just a regular tube with no vacuum inside. So you can see that the graphics, they're super similar, and because of that we cannot trust the results. Yeah. And then the test aboard of suborbital rocket. Our experiment was launched on board of the suborbital rocket VSB-30V11 from Alcântara, Maranhão, and it was expected 6 minutes of microgravity, but unfortunately the rocket didn't reach the expectations, so we also are not going to show the results on this presentation. So the conclusions are for a pulsating pipe with 5 turns, 3 millimeters inner diameter. When we try to do the tube with chemical treatment, the torso glue was not a good option because it cannot endure high levels of vibrations. So you cannot keep the vacuum inside. You're not going to get a two-phase flow inside the tube, and it's not going to work as a pulsating heat pipe. Also, I studied the interaction between glycol zero and copper under pressure, a low pressure environment is necessary because we did not know if the glycol would be strong enough to keep the hydrophobic property inside the tube under low pressure and high temperatures. We also noticed that the gravity has a big influence on the performance of the pulsating pipe, and its level decreases with the increasing of filling radio. We know from the previous studies that if you increase the number of turns of a pulsating pipe, it has less. The gravity has less impact on it. But as our tube had like 5 turns, we noticed that only with 75% filling radio, it worked in the horizontal position. It would work up in space. Also, the best performance of the tube existed with 25% in the heating bottom mode, in the vertical, reaching the value of 0.046 Celsius per watts, and for a level of 220 watts, but it did not work on the horizontal orientation. It would not work in space. The horizontal orientation for 25% and 50% filling radio dried out, as observed on the graphics, and we had to stop the test because the temperature would raise up more than 200 Celsius degrees. And the tube with 75% filling radio was the only one to work on both orientations. On the bottom heating mode, it showed values of 0.066 Celsius per watt total resistance for 300 watts and heat input, and 0.1 Celsius per watts on the horizontal. So for the next studies, we suggest that if you consider 3 millimeters diameter water as a working fluid and 5 turns, you should work with more than 50% filling radio. The results for tubes with chemical treatment were not trustworthy due to the low vacuum and for the lack of information about the interaction of glycoside and copper under low pressure environment. And the pulsating works differently when the heat input is gradually edited and abruptly edited. There's a time to get to the steady flow. Yes, so these are the reference for the presentation. Yes, this and this. And that's it. Thank you very much for watching. And now I'm open for questions.